Good morning, everyone, and welcome to the third lecture of the Sci-Tech Spin series, an outreach program organized by Indian Institute of Technology, Delhi. And I'm Dr. Tarak Karmakar, Assistant Professor in the Chemistry Department. So I'll be moderating this session. And today we have, the purpose of this weekend lecture series is to bring um, or is to connect to the students, young minds of our country, introduce them to the world of scientific research and discovery. Today's lecture is on materials that matter, and I have with me two great scientists of our country, Professor Ashok Ganguli and Professor Rajesh Prasad. So let me give a brief introduction of the first speaker. So Professor Ganguli will talk about the materials in nature and for the future. So let me give a brief introduction of our first speaker, Professor Ganguli. Professor Ganguli obtained his PhD from Indian Institute of Science in 1990, and then he did postdoc in USA. And in 1995, he joined Indian Institute of Technology, Delhi, as assistant professor. And he has been continuing research in chemistry and in material science. And his research group is interested in many research areas in materials as well as in chemistry, including nanostructured materials, applications in water purification, hydrogen generation, photoelectrochemical processes, and materials, superconducting materials. So today he'll be talking to us about materials that we find in the nature and what we can learn from those materials or those phenomena. And then inspired from those structures, patterns that we usually observe, let's say in leaves, in many rocks, or even any other materials that you see in daily life, and get inspired from those and design materials that can be used in many technological applications, such as, let's say, the spaceship, or let's say many textiles where the materials that can repel the bacteria. And so he'll be talking to us many exciting materials that are in already used in the market. And at the end, he will have some lab demonstrations where he will show how we can kind of synthesize those or design materials in the lab, followed by he will take few questions at the end. Um, Let me give you a little bit of technical description. So from 10 to 10:55, we'll have the talk by Professor Ganguly, followed by 5 minutes of question answer, and then we'll start the second talk by Professor Prasad. So without further ado, let me welcome Professor Ganguly to start his lecture. And so over to you, Professor Ganguly.
Yeah, good morning and thanks, Professor Tarak Karmakar of Chemistry Department, IIT Delhi. I also congratulate the entire team of Sci-Tech Spins, led by our Associate Dean, Professor Pritha Chandra, and Professor Somik, Professor Tarak, Professor Divya, and there are many others who are organizing this monthly interaction with young minds, those all of you who are here. And so happy to see on a Saturday morning all of you interested in science and technology. So I will just share my slides to take you through a journey and many things which we do not even think about. If you reflect how much science and technology is there in your own life at home, you will be surprised. So let me just share my slide. Can you see my slide, Tarak? Are my slides
Yes, it's clear. It's
Okay.
clear.
So, yeah. Uh, uh, Hello, young minds and our future Einstein and Schrödingers and C.V. Raman and our Marie Curie and many of those young people out there. All of you can become one day the names I said. And only thing is, look around you, keep your eyes and ears open. And there are so many things in nature that you can take pride and learn about them and invoke them and try to understand for your future. And if you are interested, you can do wonders. That's what my aim at the end of this talk is, that I should excite few of you who are here today to take up this challenge of science and do something new. That's what science teaches us, to do something new. And technology teaches us how to apply that to improve our quality of life, to improve our health, to improve sanitation. That's how science and technology go hand in hand. But it's a vast subject, you know. You all study science, from biology to astrophysics to nuclear chemistry to understanding of how the blood flows. You can understand there are so many things. And today we focus on one aspect, that's on materials. And also in materials, I'm focusing on materials which we see in nature, in lizards, in birds, in butterflies, and what do we learn from them, and how we can make those things with our brains, with our creativity, with human creativity, how we can make better things after seeing what nature has made in around us over billions or millions of years. So materials and nature and for the future means materials which already are there in birds, butterflies, etc., in whales, in sharks, in dolphins, what we can learn. And for the future means many of the things in your hand, the gadgets, futuristic mobile phone or futuristic smart screen or futuristic autonomous vehicle. That's where can we learn from nature and create materials of the future. So just a brief thing, that can you imagine what science and technology has done if you think for just a moment that 800 years back, just 800 years. You know, the world is how many billions? 4.5 billion years old. Only 800 years back, we did not have the buttons which you are having on your shirt. 500 years back, we had no thermometer, no pencil with which you write. People did not have that. 300 years back, if you go back in time, there was nobody in the world who had traveled on a train, because no train existed 300 years back. 200 years back, there was no electricity, which all of you in the morning put on the switch and, you know, geyser turns on hot water. All that human brain has made it possible through science and technology. Imagine, without electricity, can you work today? Anything can you do in school, college, or in your daily life. There was no automatic watch 100 years back. There was no color TV 70 years back. There was no mobile phone 50 years back. And there was no internet. Can you believe a world without internet? All of you have grown up in the world of internet. Just 40 years back. That means when I was going to school, like you, there was no internet, right? But even now, what are the challenges? There are many things. Scientists are working and breaking their heads all over the day and night. There is no HIV vaccine. The world knows HIV for a long time now, but there is no vaccine. So a lot of people in the world, in different labs in India, China, Japan, United States, they are working to find an HIV vaccine. There is no medicine for cancer. So many people die of cancer. We have cancer therapy, but we don't have an answer for cancer. So all these are only two things I told you, which we don't have an answer, and somebody has to work on that. But like that, there are hundreds of things today that we don't have an answer, and somebody has to work like you in the future. Imagine how science grew in the 15 1600. There was one man, Galileo. Alone he made the thermometer, the compass, the telescope, and pendulum clock. One man, with his creativity, with his mind, with no machines available. There was no engineer available to him. Everything he did himself. And now we know things which are common in your house like light bulb, telephone, microwave, refrigerator, air conditioner. Name all these things. All has been due to the creative of the human mind. This is what is science and this is what is technology. Now, these are things which you can see with your eyes. There are things you cannot see with your eyes. And that's why you need to know the length scales. That means our eye can see something like as small as say 0.03 millimeters, somewhere here. But below that, all these numbers I show you, micrometer, nanometer, picometer, none of you can see. But there is a whole world there. And that world can be brought alive if you have the technology to see things small. And we have them today. Similarly, what about Earth's radius? We know, we have measured long. We know the distance between Earth and the moon, the Earth and the sun. How do we do it? They are so far away. We are getting signals from extremities of the universe. How do we do that? We have the world's latest electron microscope, which shows you the atoms and now even inside the atoms, less than a nanometer. These are the high-tech gadgets of today. The radio telescope shows you how we can access information from the edge of the universe. These are the world's great machines of today. To see something very small, to see something from very far, both are possible with the advancement of modern science and technology. But let me come to materials in nature. You see, polar bears are there. There are whales. There are penguins. Can you imagine polar bear does not need a blanket? You use a blanket at 10 degrees Celsius in Delhi. But a polar bear is in Siberia, in the North Pole, in Greenland. What? It has no blanket. Nature has developed the material for itself. That's the fur on itself. Similarly, penguins are in Antarctica, always frozen. But have you seen a penguin with ice on itself? No, because nature has given it a coat, a material which does not allow ice formation. Similarly, whales have some unique characteristics. Sharks have some unique characteristics. All that nature has given for them to survive. Otherwise, how will they survive? Some fishes can go to depths which no man can go because you will die with the water pressure above you. So we have to wear special suits, special diving suits when we go underwater. But those fishes or those marine animals don't need that because nature has allowed them that technology naturally. And human beings are learning those technologies, how to survive in the depths of the ocean, in the outer atmosphere. And that is our creativity, that we can fast forward what nature does over thousands of years. We can fast forward in few years and achieve that which nature does over several thousands of years. So let me show you a movie on what are fireflies. All of you know about that. The fireflies have this chemical inside which is called luciferin. And luciferin is a molecule, it's a protein. That luciferin takes up oxygen and becomes oxyluciferin. And when it comes back to luciferin, it emits light. That's the science, that's the chemistry that one has learned. Those who do research in such things have explained how oxygen comes in. The luciferin, in the presence of the enzyme luciferase, gives out light, and that we see in the fireflies. Our normal bulbs waste most of the light energy, but in the luciferin or these fireflies, 100% of the light is converted. This kind of light can also be seen in many marine organisms. That is to attract prey or to chase away predators. They can change their color depending on whether they want it to be identified or not to be identified. If you go to Australia, there is a beach where it is reddish in color. That's also due to some organism. At night, it gives out light. It's called bioluminescence, like the fireflies. Such beautiful things now human beings can make in the lab and use for applications. For example, we can make probes, luminescent probes, which we can inject into a body And then from the light which is coming out, we can find out where is this light coming from. And if that luminescent probe is attached to a cancer cell, I can find out where is the cancer cell. This is modern technology. Learning from luminescence, learning from luminescent materials, applying into modern technology. So these are other organisms which also show bioluminescence. So what is this bioluminescence? In a normal light bulb, heat, the tungsten filament is heated by electricity. This heat is converted into light which you see. In a normal other fluorescent molecules, you can see there are many fluorescent molecules in a chemistry lab which give out light. That is called fluorescence. In a bioluminescence is different from fluorescence, because in fluorescence, a photon has to be accepted by the molecule in the chemical to go to an excited state, and then it comes down and then releases light of a different wavelength. And this is called fluorescence. In a organism where there is a change in the chemical composition, where luciferin was becoming oxyluciferin, which is in an excited state, and that emits again radiation which you see as light. The difference between the two is this has very high efficiency. That's why all the fireflies, whatever the light comes, it's like 100%, and it is cold light. There is no heat associated with it. So this is the luciferin molecule, those who are interested in chemistry. So how in your classroom chemistry, you can connect to nature and understand what's happening in fireflies. If you understand these molecules, and if when you grow up, you are in college, you will understand by these molecules emit certain wavelength of light. And there are many molecules. I told about luciferin. There can be derivatives of luciferin. There can be other molecules which are there in organisms naturally, and we can have artificial molecules which we can synthesize in our laboratory, learning from these molecules. And as I said, one of the key applications today in the world is to solve cancer problems. So first of all, you must know where is the cancer. If you can locate the cancer accurately and you can do some therapy at that site and kill only the cancer cell, then that is the great thing. So how, this is one example how one does it, that you either send a fluorescent dye or a nanomaterial which will shine light, which will give out light. That fluorescent molecule should go and attach to the tumor cells. And then you can use what is called near IR radiation. Near IR radiation is light which has a wavelength of around, say, 700 to 900 or 900 to 1100, depending on what kind of near IR radiation you are using. A very common radiation used is around 808 nanometer. And how do we get it? This is because we have a laser. This is man-made. These lasers we can use, and we can kill cancer cells after sending in the nanoprobes inside the body, and those nanoprobes go into the tumor inside. This is an experimental case where a tumor is created in a mouse, and then you inject the fluorescent molecule to image where is the cancer cell. Once you image it, you know where it is, you can kill those cancer cells specifically without killing your normal cells. So fluorescent dyes, which are there in the fireflies, you see, understanding them brings up understanding which we apply in our cancer medicine, in nanomedicine, etc. Similarly, this is another example of nanostructured materials in nature. This can be today called as nanophotonics. So this is a butterfly which is yellow in color. It does not show any nanophotonics. This one shows, this is blue in color, it appears blue in color, but if you shine light, it appears brown in color. Now, why is that? Something which appears blue like this is the real picture of the butterfly, but it becomes brown in color whenever it wants to be. There is actually no blue pigment in this butterfly. The butterfly's blue color comes because of those fine structures that you see under the microscope. This is a scanning electron microscope image which shows those fine structures. And these fine structures can be changed by the butterfly. In one distance, suppose it will emit blue light, But when the distance changes, which the butterfly can do, when it moves around, it will give you another distance. When light strikes that, it will become brown in color. So blue and brown, this butterfly, is because of the butterfly's wings having these pores whose size is changing. Because of the movement of the butterfly's wings, it can become brown or it can become blue when it wants. And this is nature's way of protecting the butterfly. When it wants to protect itself, it hides in the bark, and the brown color becomes prominent. When it wants to mate, it flies with a very beautiful blue color and to attract its mate. So that's how we learn that in nanostructures are present in natural materials like natural organisms like butterfly, and we learn from that. And from that, now we can make materials with different particles with different sizes. You see, if I have colloidal fibers with particles of around 220 nanometers, I get this color. If I change the size of the particles to 246 nanometers, I get a different color. So this we learned from nature, which is called biophotonics, that is light emanating from biological organisms. And now we are putting in an artificial or an inorganic material which is made in the lab but uses similar concepts. This is another video of showing in nature what something exists. That is, you want to climb walls like a lizard, there are structures under its leg. These are called hierarchical structures. That means you look at one microscope, you see mesostructures. You look under more carefully, you will see microstructures. And similarly, you can see nanostructures. So these nanostructures, they create capillary forces. And that and the van der Waals forces, which you have studied in school, they allow one to grip on the wall. So you can now make artificial materials and climb the wall using polymers, which have similar hierarchical structures as we learned, which are there in geckos. Gecko is another name, Americanized name for a lizard. And under the lizard's uh, feet, if we take a cross section and look under the microscope, you will see hierarchical structures. What does hierarchy means? You will see very small structures and then semi-large structures and the large structures. How carefully are you looking? That matters. And now we can make hierarchical structures in the lab. So depending on the type of the organism, if it is a heavy organism, it will have more legs. If it is a light organism, it has less number of legs. Okay. Now, this we make in the lab. So people have made in the lab using polymers. Similar structures which can allow one to grip on surfaces. These are made on polymers and are hierarchical structures. You can see these standing on. Now, similarly, but at another application, you can see on insects or organisms which walk on water. If you look under the legs, under a scanning electron microscope, and that means you are magnifying the image by 30,000 times or 50,000 times, then you will see these micro hairs. And if you zoom in further using more advanced microscopes, you can see nano grooves. On those, each micro hair will have several nano grooves. And what happens in these nano grooves, air gets trapped. And when air gets trapped, they can walk on water. That's what you do when you learn swimming. You tie a tire filled with air on your waist. That's what your parents do and drop you inside the swimming pool. That's how kids learn swimming, because the air allows them to float. So these ants or these organisms are having air trapped within these nano grooves, which is under their feet, which you cannot see with your naked eye, but with modern technology, modern understanding of science, and applying it through our devices like the microscopes, which are very advanced today. And then we can see all these structures and we can plan ahead. This is also seen the same way, hierarchical structures on a lotus leaf. Not only lotus leaf, many thick leaves. You will have many plants in your house which have very thick leaves. Whenever you have thick leaves, if you take a cross section of that leaf and look under the microscope, You need a powerful microscope more than the optical microscopes normally used in schools. You may have to go to a scanning electron microscope. What is the difference? The optical microscope uses natural light. The scanning electron microscope uses electrons. And what is the difference? Electrons can have very low wavelengths. The simple concept in science is the lower the wavelength of light you use, you can see smaller and smaller objects. And we can tune the electrons to our choice of the wavelength. And that is in our control. So we can vary the wavelength of the electron. But natural light wavelength is fixed. It comes within a range of 400 to 700 nanometers. But the wavelength of the electron is our control. We can change the voltage applied to the electron being generated, and we can modify the wavelength of the electron, and hence we can go to smaller and smaller sizes. With electrons having smaller wavelengths, we can see objects with smaller sizes. So we can see all these nanostructures in the lab. So these nanostructures, what they do, they are called super hydrophobic surfaces. What is hydrophobicity? Something which does not like water. And super hydrophobicity means really extreme dislike for water. That means if you put a water droplet, it will run away from the surface. So imagine you have a tablecloth and you put a droplet of water. Normally, what happens? The droplet will spread on the cloth. But if you have a tablecloth made of such material, the water will just fall off the table because it will run away from the surface of that tablecloth. So these things are now available in the market, not only on cloth, it is available on glass. So you can make smart glasses using nanostructures, which one can make in the laboratory on polymers, on glass, and many substrates. You can make on textiles, on shirts. So what will happen if you have these kind of surfaces with a nano finish, we say in textiles, then what will happen? Water droplets, suppose you rinse it in water, put it in in a bucket, and then you take it out and you just give it a jerk, all the droplets will fall off. That means the shirt will get dried very fast. Now, where can this be used? This can be used and has been used for, say, the defense forces in the mountains on the Siachen Glacier. This was one of the projects with DRDO, maybe IIT and ARCI Hyderabad, and you can see me holding a jeans. This technology has been transferred to a Bangalore-based company, and then many socks, jeans, and other innerwear and jackets have been made where there is a nano finish, and you can use it for many purposes. It is available commercially also, and many companies are selling this. Now, this is shark skin is also super hydrophobic because of the special structures. You see on the left side, you have the special structure of shark skin, whereas if you look at normal fishes will not have this structure. And that is why this special structure of the shark skin does not allow bacteria to form. The bacteria will flow off from the shark skin, and you will not see any colonies of bacteria. The left one is the nanostructures on the shark skin. And so using this technology, there's a company called Sharklet, which makes nanosprays and nanofilms, which will give rise to antibacterial surfaces. So of course, you can look under the SEM. This is the SEM, which shows all the structures like I showed earlier of the plants, etc. Or you can take any skin of the shark or a fish or anything and look under the microscope. This is a SEM picture, how it is taken. But a shark skin, which I was talking, this is the company Sharklet Technologies, which used this knowledge of a shark skin and made a polymer which has a surface which you see looks very much like the real shark skin. And because of this unique surface, if you put bacterial cells on top of a polymer without the nanostructures and a polymer with the nanostructures, after some time, you will see bacterial growth on the polymer which does not have the nanostructures. But the polymer with the nanostructures, which look just like the shark skin, has very few bacterial cells. That means it is an antibacterial surface. So where it can be used? It can be used at the bottom of the boats, ships, submarines. If you put this polymer, the ships or submarines are always in water. and hence they can get all these bacteria and all that other things, and it is called biofouling. Anything which is in water for a long time, it gets it's fouling causes holes in the surface of that boat, etc. So this is a big naval problem, and this naval problem can be solved by using materials like this, where that will not allow bacterial cells to grow on the surface. Now, let me come to materials which withstand extreme high and low temperatures. So I'm switching from natural materials, now some materials made with polymers in the laboratory and can be used for making high and low temperature. So normally, a typical heat resistant material has three layers. There's an outer layer which is made of some polymers, right? The polymers mentioned, these are commercial names called Nomex and Gemini. Then there is another layer which is called the moisture barrier, which prevents water, water vapor, pathogens. And there is a third inner layer, which is called the thermal liner. And the commercial name normally used is Caldura, but there are others also. I've just used one name, and which gives thermal protection. So this three-layer system prevents a body to be, for fire to touch a body which is wearing such a surface. So these polymers I was talking, say Nomex is an aromatic polyamide. So in chemistry, you must be studying these kind of molecules. So polymers are made by the condensation of monomers. So you start with a monomer which has a group which can bind to another monomer like a carboxylic acid, or you can make an interaction with an amide group formation. So you can have a polyamide, you can have a para-aramid. This Kevlar is also used in bulletproof vests, etc. So many of these are patented by companies where they were first made, and they are used a lot either in combination with another polymer or multiple polymers. It depends on the application which you are looking for. So suppose this application is for fire, so some of these can withstand up till 1000 degree centigrade. So you can see this. These are commercial materials which are available, which can withstand even 1000 degree centigrade and are also lightweight. So you can use these materials to make gloves. Suppose you have to handle chemicals inside, like in our laboratory here, a student is using those gloves to handle chemicals inside a furnace, which is at say 1000 degree centigrade or 900 degree centigrade. So we can withstand 1000 degree centigrade. But suppose you have to use the material for a spaceship which is doing re-entry. So this is known for shuttles like Columbia, Endeavour, etc. Those of you who are fans of space travel, these shuttles re-entry, because earlier days we used to have rockets going to space and then they used to fall in the sea. But these shuttles land on the ground just like an aircraft. And when they do re-entry, the nozzles reach temperatures of around 1500 degrees centigrade. And this nozzle, where in this picture, you can see different colors. The different colors actually tell you about different temperatures on the body when the aircraft is re-entering. The velocity at which a space shuttle re-enters is around 17,500 miles per hour or something like that. That is like 27,000 kilometers per hour. At that speed, when it re-enters the atmosphere, and outer space, there is no atmosphere. And then it enters the atmosphere where all kinds of particles are there. There will be friction. That friction causes a temperature increase. And different parts of the spacecraft have different temperature. The nose cone and the edge of the wing has the highest temperature. That's where you need to put some material which can withstand temperatures of around 1500 degrees centigrade. And some of these are made of composite tiles, not one material, but many materials put one on top of the other to uh, withstand these temperatures. So some of these materials at the nose cone, you use reinforced carbon-carbon coating. And the blue region, which is a large part, you use surface insulation tile. And of course, the yellow region or the green region have much lower temperatures. So to show you what is this black region, this composite tile, you see, it is made up of so many layers. You have aluminum substrate, you have a silicon rubber, you have a Nomex, which we mentioned. Nomex is that heat resistant polymer. And using that, when you make this tile, which is shown here in this video, this black side is outside, and that black side is the one which can you can use the high temperature. So you can see once more the black part is where the aircraft, when it enters, that tile faces the high temperature, which is it is withstanding while re-entry. And you know, if even one tile goes off, what happened to one of the shuttles, because one of the tile was dislodged when it was taking off, and that was the problem. That was that was the spacecraft which Kalpana Chawla was there. And while re-entry, the tile fell off while it was going up, and while re-entry, that was the one which created the issue, and the spacecraft went up in a ball of fire, right? So there is also, you have, is there any question?
Yes, Professor Ganguly, I have collected a few. Would you like to take two
Yeah,
or three?
quickly. Yeah.
Okay, so somebody, Tanvi asked, sir, is waterproof shirt such an example of something? I think she was trying to mention the hydrophobicity and
Yeah,
stuff
yeah.
like that.
So there are shirts available. It is like you have a surface finish. So waterproof shirts are like that. But the one typically we are what I showed, which has a super hydrophobic coating, which has a nano finish, that is meant that it dries fast. Actually, you can even add some silver nanoparticles with that, and that is also been done. Then what it does, it not only allows you to dry fast, it also allows it to become antibacterial. So that shirt need not be washed very often. So suppose you are in Siachen Glacier and you are, it's a soldier cannot keep washing his shirt, but he can wear that antibacterial shirt because it will not allow any bacteria to grow even if he is wearing for a long time. So those kind of shirts, etc., and socks have been made where you have not only super hydrophobic coating, you have silver nanoparticles embedded textiles which are being sold, and they have been made into yes.
So the next question is, why don't circlet pools exist? The question asked by Anu Gitika.
What is it? I could not follow you.
Why don't circlet pools exist? I don't know.
I can't get the word. Circulate?
Circlet pools, like swimming pools.
I did
Anyway,
circulate.
this one we
Where?
can
Where?
we can drop for the timing. So, can medicines be made from nanoscience? It's a
Oh
general
yeah,
question.
oh, lots, lots. The subject is called nanomedicine. It's a huge subject. I just showed you one where you are using there is a nanoparticle which is loaded with a dye, and it is loaded also functionalized with some chemicals, and it is sent into the body, and that nanoparticle with the drug and that nano functionality goes and attaches to a specific place in the body where you want to go. Say it goes to the liver, kidney, and using it can have a magnetic particle so that you can track the particle from outside. You can move the particle using a magnetic field. So many such things are done. It's a huge field of nanomedicine.
Okay, then I think let's continue. We will have few more questions after your talk.
Okay, so I was talking of high temperatures protection. Now let me come to low temperature, because where is low temperature required most? Suppose we get low temperature. If you are in Delhi, low temperature will be 5 degrees centigrade. But suppose you are in Chicago, you may land up with minus 20 degrees centigrade. But even if you go to maybe Greenland, you may land up with minus 40 degrees centigrade. But even lower, there are places people are going where even lower temperature. For normal low temperatures, you can use this kind of fleece jackets, etc., which are again made with polymers. You see, polymers are again very important. So you are using a polytetrafluoroethylene based polymer which has a fluid inside, and these PTFE based materials have been used for uh, not allowing low temperature reach your body, so it controls the low temperature. You can use polyester fibers, and these polyester fibers are used in many fleece jackets which you buy and wear for low temperatures, but these are not the real low temperatures. The real low temperature is when you go to outer space. So look at the temperature on the surface of the moon. You know, all of you know when the first landing was done in 1969 by Armstrong and Aldrin. They landed on the moon, and the temperatures on the moon can vary between 120 degrees centigrade in the daytime and minus 175 at night. So as you know, most of the moon landings are done at night because 120 degrees is very difficult to handle. Okay, so the thing is, what kind of suits one will wear? So one has to design materials for such people who can go into outer space. Not only that, that was in 69, but even today, the International Space Station, ISS, is there in the upper atmosphere. It's at 400 kilometers from our sea level, right? So this is actually, moon is much far away. Moon is maybe 390,000 kilometers. But the temperatures, you see, even at 400 kilometers, the temperature is minus 156 to 120 degrees centigrade. But these people are doing a spacewalk. That means they can handle very low temperatures, and they can also handle some high temperatures. So what kind of materials one can use to make low temperature things? That's important. So you look at the space suit, it is made of 14 layers, and each one has a job to do. You have an inner garment liner, you have liquid cooling garment made of nylon, spandex, so many types of different materials. So you see the world of materials. For one space suit, 14 layers of materials are being made. There's a pressure garment. There can be, you have to take out your urine or something while wearing the space suit. So there has to be some tubes, etc., going through. There will be lots of sensors inbuilt inside the garments. Those are called, or today's world, we call them wearable textiles. That means how you interface sensors with textiles, sensors with polymers, because so many work is being done by sensors. You cannot, somebody is talking to you, you have to see it on your visor. That is what helmet you are wearing. The helmet is having so many sensors. So there are so many things, but let me talk only of the garment here, which is made of 14 layers. And you can see the six, there is dacron, there is nylon, there is aluminized mylar, there is spandex. So if you are a student of materials, you will know all these things, all these polymers, how are they made, how are they generated in the lab, and what temperatures they can withstand, what flexibility they have. Because it's not only temperature, you have to have some flexibility, you have to have strength, it should not break. Then it should not leak out water, or water vapor should not come in. There are so many other aspects to this garment which allows one to do a spacewalk today. And it is unbelievable. So many people have gone up and down. I think close to 200 people have visited the International Space Station, which is still there. And many people go. And at the same time, the craft which goes from Earth can go and attach itself to the International Space Station. So these are, if you are a student of chemistry, these are the things which one learns in lab. So when you are reading chemistry in high school, these structures are taught to you. Sometimes you feel, why am I reading all these aromatic rings, so many carbon chains? You see where the application is. All these have applications, and not applications for few rupees. There are billion-dollar applications. Imagine floating an ISS. One country cannot do it. That's why there is a consortium of so many countries, US, Japan, Russia. They all put money together to keep the ISS aboard. And then people go and visit and do experiments. So why do they want a spaceship up there? Because you can do experiments there. You can do experiments under microgravity. You can do experiments at those low temperatures. You can do experiments where oxygen is not there. On Earth, it's very difficult, right? But look at the molecules that you have, and you should read about them. What is Kevlar? What is Nomex? What is Dacron? What is nylon? What is spandex? So much, the world of polymer materials. And there are composite, carbon-based composites, which is made in the nose cone, which takes the maximum heat. What is that carbon composite? You must ask yourself when you are in class next time and find out the structures. Okay. So now let me go to the next slide. So I was talking about outer space, and I was talking about the material people need to be in outer space. Now let me ask you this question, that on Earth, we are always talking about oxygen because we are inhaling oxygen. Suppose oxygen had not been there, we would not survive. But is it true on the moon? No. On the moon, those gases are there which we buy, we make in the lab, and it is so expensive to buy. Suppose you want to buy helium. Helium we have to import from United States. In India, we don't make helium. Now, if you want to make helium gas, is available for free on the surface of the moon. Neon gas is available for free on the surface of the moon. In India, if you want to buy, or on Earth, if you want to buy helium neon, you pay huge amount of money because it has to be created. It has to be made artificially. It's not easy to get. Very, very low amount of helium is in Earth's atmosphere. Very, very low amount of neon is in Earth's atmosphere. Our atmosphere is full of oxygen and nitrogen and maybe some amount of carbon dioxide, etc. But on the surface of the moon, the maximum amount of gas is helium, neon, hydrogen, and argon. And to some less amount is methane, ammonia, and carbon dioxide. And oxygen, no, it's not there. And so you can't breathe. So everybody who goes on the moon has to take his own oxygen. But oxygen is there on the moon, not in the atmosphere, but in the rocks. So that's the future. In the future, if human beings have to live there, people have already thought about it. How will we generate our oxygen? We cannot take oxygen from the earth. We have to get oxygen from the earth of the moon, from the rocks in the moon, where the oxygen is trapped. That's again materials. What is that rock? What is that oxide? It is present as an oxide material on the surface of the moon. If you dig deep, you will get all those. And so if you have an oxide material, I can do some experiments and generate oxygen. That's for the future. But you'll see how interesting. On Earth, you have those gases which are not there on the moon. But if I have to create an environment like moon, where I have helium and neon, and I want to do some chemistry, how to do that? That we can do in what we call a glove box, which has a chamber where I can control my gases the way I want. I can put my hands inside. I can do reaction inside. I can lower the temperature if I have a refrigerator inside. So you can make devices. This is man-made. We are creating an atmosphere where we can create materials like we can easily create. So this is a glove box, how one can work. You have chambers. You can control the meters of oxygen, how much gas I want to put in, which gas I want to put in. For that, I have cylinders. So this is an argon cylinder. I can put in argon, I can put in helium, I can put in neon, but I have to buy them on Earth. They are very expensive gases, and create a chamber in which one can work with argon, one can work with helium, one can work with neon, and one can control the reactions. And then we can, if we have an ability to also lower the temperature, like on the surface of the moon, or may not be the surface of the moon, that is very low, but at least minus 40 degrees, minus 50 degrees, which is possible using refrigerated systems which are available, then I can do reactions in my lab which one can mimic in the on the moon easily. So on the moon, I don't need all these devices because you have available neon, you can available helium, but here I have to do it inside. I can create vacuum using pumps. These are called oil diffusion pumps or mechanical pumps, and that human beings have made several types of pumps to evacuate air. Suppose I have to take out air because air is all over our place. So in these tubular chambers, I can create so-called vacuum using these pumps, and I can do reactions in vacuum inside these chambers. These chambers can be of glass. These chambers can be of quartz, that is silica, which we are using here, which is being shown. But these chambers can also be of some metals. I can use metals like tantalum, niobium, etc., create vacuum and do reactions inside. So now let me come to a new phenomena of materials called superconducting materials, which show levitation, that is floating in air. So uh, you all must have heard of maglev trains, which float above the ground, okay? And that is possible by using superconducting tracks. So how one can make these superconducting tracks, one can see that you make this material is uh, superconducting below 90 Kelvin. That means at room temperature, it will not show levitation. You have to cool this material below a certain temperature. And there are different materials possible. The material which we are showing is based on yttrium is a element in the periodic table with the symbol Y. So yttrium with barium and copper and oxygen. So you have to mix in the right proportions. Then you can get this material, black material on top. There is a magnet which is floating, and we have put liquid nitrogen because it can only do this below 90 Kelvin. So you get 77 Kelvin with liquid nitrogen, and then this disk will float on a track. So this is what is happening. The magnetic lines of force of a magnet and the superconductor is repelling those lines of force, and that is used, that can be used for a maglev train. So a maglev train, actually, the commercial one only runs in Shanghai. People have made it in Germany, in Japan, but it is not, it's only for experimental purposes and for research purposes. The only commercial train where you can go and sit is in Shanghai. If you go to Shanghai airport, and then you can take the maglev train. It travels at a velocity of 450 kilometers per hour, and it is an 8-minute drive to the center of the city if you take this maglev train. And the basic phenomena is you can use levitation, and levitation is basically repulsion, which you can create between two magnets or a superconductor and a magnet, because the superconductor below its transition temperature will expel the magnetic field, and that will cause it to levitate or go higher above. And since there is no friction because the train is above the track, it can achieve high velocity, and there is no movement, etc. It is very smooth ride that you will get. Now, coming to futuristic materials, imagine computers of 1990. This is a computer of 1990. It had these chips. That time, the feature size was around 14, 15 micron. The feature size means a chip has many, many circuits. That's what is an integrated chip. Those days, each circuit element, which is called the feature size, the smallest was around 14, 15 micron. The world has changed so much dramatically. Those computers were much slow. Today, your mobile phone is so fast. Your laptop is so fast because of the modern IC chips made with materials and made with processes where you can make very tiny, very, very small features, very, very small interconnects. And that's modern technology. How these chips are made, starting from sand. From sand, you make silicon. From silicon, you make single crystal silicon. From that single crystal silicon, you make silicon wafers. And from silicon wafers, you put the circuit elements on top. It's a process which has been done in industry like Intel and TCMC, Intel in US, AMD in US, and TCMC is the world's largest chip manufacturing organization today. It's in Taiwan, right? So this is TSMC in Taiwan. This is a person who made that company. And in 2019, the feature size was 5 nanometers. To make it smaller and smaller, that's what the world is trying, so that you can have more information storage, so that your laptops become lighter and smaller, your pen drives can store more information. How does that happen? It all starts with silicon. And silicon starts from silica, from sand. It's all material science. From sand to silicon to single crystalline silicon to silicon wafer, and then making the circuits on the silicon wafer. Modern technology also teaches us, this IBM has shown many years back in the laboratory, that you can write with atoms. What you do is you write with a pen. The diameter of your pen or pencil, the sharpest pencil, will be about around 0.05 millimeter, right? But with atoms, when you write, you're writing at 1 or less than 1 nanometer. And that means you can write millions of times smaller with atoms than with your pencil. So you can cramp in much more information. With molecules also one can write. That's called dip pen nanolithography, like how your desk jet printer works. This works like that, and it can imprint molecules on a surface. So I can pattern my surface with molecules. This is a cheaper technique. The atom deposition is a very expensive technique, but the world's first atomic hard disk has been made in 2016. The technology was known in 1989 in a lab, but to make it a hard disk made of atoms took several years and was launched in 2016. But with molecules, it is much easier. So you can take liquids in which molecules are there and which you can pattern on a surface. And this is done by Shad Mirkin, Northwestern, and who first showed this thing. We can now have biochips, the integrated chips in which electrons run and give all the connectivity. You can have biochips, well, fluids flow, and you can make devices like this handheld watch in which drug molecules are there, which can be injected in your body through syringes which are behind the surface of this watch. And when you wear this watch, it injects through a program and you can get the medicine. Mostly it is used for diabetes, and because diabetes in children, you need programmed supply of insulin, and this can do that. So what does one can do? Like this is a little larger version in our lab. This is at millimeter scale. You can do at nanometer scale, you can do at micron scale, you can do millimeter scale, where you can flow liquids and you can interact liquids. And this is called you can use a biochip or a chemical chip where you can do reactions within these patterned channels. And this is one reaction of where light is used to catalyze a chemical reaction inside these channels for converting an organic pollutant into a normal non-pollutant. Okay, but in future, now for young students, the future, you need materials for sustainability. So semiconductor nanocatalysts are used for converting light into electricity, photoelectrochemical water splitting. Also hydrogen. Hydrogen is considered the future fuel, clean fuel, because hydrogen when it burns will give you water vapor. So these are things which as a young person you should know, that what are the materials. Everything that you do now, you have to take environment into the picture. You see the pollution all around. So you must not make materials which pollute, or you have to make materials which remove pollution, which remove carbon dioxide. Which can you make materials which generate hydrogen for fuel, or can you convert waste to wealth? This is the future thing. So this is how from sunlight you can convert into fuel or electricity. You can use this kind of electrodes where it's called a photoelectrochemical process, where you can generate oxygen and hydrogen. The hydrogen can be used as a fuel. It's a clean fuel. So you can now, people are making cars which are running on hydrogen, or you can use oxygen to run a fuel cell. A fuel cell then can be used for power generation, right? So this kind of catalyst, semiconductor catalyst, nano catalysts are made, which can produce hydrogen and oxygen, and you can use both oxygen and hydrogen. So one short movie in a laboratory, what we do, we make a semiconductor catalyst, we are putting on an electrode, and this electrode then we will connect to another electrode, because you need at least 2 electrodes to make a cell. We'll pass current, and then so this is a photoelectrochemical process. Will pass current. Also you can shine light. So both light and current will generate hydrogen and oxygen, and which you can visualize with as the hydrogen and oxygen are coming out, air bubbles. You can also monitor through a computer. It is showing how much gas is being liberated through what is called current voltage plot. You can convert it into hydrogen, how many moles of hydrogen it is producing, and you can see physically with your eyes that bubbles are coming out from that electrode assembly that you had, which is you are basically splitting water to produce hydrogen at one electrode and oxygen at another electrode. The, the last thing which I want to show you is how you can convert paper waste in a very useful material, which is a nano material. So we use paper waste and then bleach the paper from the trash and then acidify, and then you get this what is called nanocellulose. And nanocellulose has a lot of applications one can use. So we have made films out of this, and they are freestanding films, but you can use for many other applications too. This is a nanocellulose film from paper waste, but yeah, it has got several other. You can use nanocellulose as an adsorbent. So you see it is put into this dye material. The nanocellulose, this white color, picks up all the dye, and the water is more pure. It can be used as a piezoelectric material. It can be used as for water purification as a membrane. So there are many, many applications. So for future, all students, remember, sustainability is very important. Zero waste is very important. All of you should be talking. No process should be creating more waste. The world has already a lot of waste. The future is going to be very tough. You need clean water, you need clean air, you need electric mobility. These are the things of the future. And for all of them, you need novel materials, either composites, polymers, nanoparticles, nanomaterials for drug delivery, most of them. Finally, my last slide, this is for my young friends. You know, all of us have a lifespan of 70 years, 70, 75 years. So do what you want to do. Enjoy this life, because whatever subject you choose, like I am now 60, I still enjoy the subject of chemistry, materials, physics, because these subjects are all interdisciplinary at the borderline. So if you like to do chemistry, physics, material science, engineering, choose that subject. If you like to do music, dance, choose that subject, so that you enjoy all your life what you like. You should think early, prioritize what you want to do, manage your time well, but you have to be put in hard work. There's nothing which you can do without hard work. All of us have 24 hours, remember. But in that 24 hours, somebody becomes Elon Musk, the founder of Tesla, or somebody becomes, Mukesh Ambani, somebody becomes J.R.D. Tata, all, and you know they all have that same 24 hours that you and I have. But what is difference is how probably they plan their life, they plan their day, and they choose their problems, what to do, choose their sport, what to play, when to play, choose their movies, when to watch, what to watch, and so apportion your time properly. And once you know this is what I like, then go for it. You have to be persistent. Remind yourself every day is a great day. Remind also yourself every day is one day less in your life. Always be positive. There are many things to complain in this life, but if you are positive, you will overcome those challenges. Have good friends and have a good sense of humor. Enjoy and have a good time. Thank you very much.
Okay. Thank you, Professor Ganguly, for a wonderful talk, and I'm sure many students they have they have enjoyed it thoroughly, and now they are more curious than ever
I just
about this.
wanted to show some of the acknowledgements of some of the movies, so any of you can see these acknowledgements. And my students who helped me a little bit in making some of these slides, Manisha, Priyanka, Nitika, Prabuddha, and Shalini, they're all my PhD students. Thanks.
Yeah, thank you, Professor Ganguly. So, can I take like 3-4 questions before we move on to the next?
Sure.
Yeah. So somebody has asked a very funny question. How can we wash hydrophobic shirts when it is full of dirt?
Uh, how can you?
How can we wash hydrophobic shirts when it is full of dirt? I think
Hydrophobic shirts when it is full of dirt.
yeah. It's a
No,
funny
so
question.
dirt means what? Dust particle, no? Some
Yeah.
particles, inorganic particles, right? So either carbon or it can be some silicates. Dust means silicates or some particles, right?
Yeah.
Okay. So even though it is hydrophobic, there will always be on a leaf also. If you look at the leaves in your house, there will be some thick leaves, they will have less dirt, and there will be some leaves which will have accumulate more dirt, right?
Yeah.
So that
Yeah.
tells you the difference on the surface of the leaves, right? Similarly, if you have a hydrophobic surface, it may have some dust or it may have some particles, but it will be always little bit less than the other particles, other leaves, non-hydrophobic.
Yeah.
Am I okay in this question?
Yes, I think it's fine. So the next question from Kavya is the fluorescent dye technology to locate the cancer cells being used today. I think related to cancer cell imaging.
Yeah, yeah. It is being used only. See, when you want to use it, you have to take a lot of approvals. Anything to do with human body takes a lot of approvals. You have to go through. So many of these are approved for animal studies. So you can do them in mice, this, that. And then some dyes have been approved for biological applications. So there are, say, one or two dyes which are allowed, which you can inject, etc. And it is given in the body. Yes, it is possible.
Okay. So the next one is from Ashutosh. Doesn't the laser light damage body cells along with cancer cells while treating cancer?
Yeah, it's a very good question. So if you read any paper, that we use a certain kind of laser light. The
Hmm.
reason that we use a certain kind of laser light is that it does not damage the other normal cells. So that's why you see we are using a 808 nanometer laser. That's a near IR laser. So the
Hmm.
near IR laser does not damage uh, uh, to a significant amount the normal cells, but it will do the job for the cancer cell. So you have to
Uh,
choose appropriate laser beam with appropriate wavelength of light. You cannot use any light.
yeah, it's true. And probably a quick question from Partha. What is the main reason when a duck swims in a pond and the whole body gets dyed? I think it's related to hydrophobicity.
Yes, yes.
Okay.
The surface
Then,
is clean, right? That's what it's in water, but the surface can be it shakes its feathers and all the water goes,
yeah.
right? Okay.
Yes, yes. So then I keep other questions for the question answer session that will be from 12:20, I guess. So I again thank you, Professor Ganguly, for an
Okay.
excellent talk.
Okay.
And then
You
we move on to the next one.
can
Thank you.
unshare my screen. I can.
Yeah. Okay, great. So
Thanks.
thank you, Professor Ganguly.
Thanks.
Now I'll move to the next. Let's move on to the next speaker. We have Professor Rajesh Prasad. He's a professor in Department of Materials Science and Engineering at IIT Delhi. And Professor Prasad did his, I mean, a little bit of his background. Professor Prasad has obtained his PhD from Cambridge University, and then he joined at IIT Delhi in 1995 as an assistant professor. And from then, he has been doing research on material science, and his research group is currently working on many aspects of materials, let's say starting from crystallization, uh, crystal deformation, and the new techniques, how we can design new materials. So today he'll be talking us about sinking of ships and falling of aircrafts, the science of deformation. So probably you have already got the like so the punchline, how and why the Titanic sinked. So probably you'll get all the kind of science behind this kind of accidents, as well as many exciting things related to materials, design, and deformation, and how they're relevant in our daily life and technology. So with this, I'd like to welcome Professor Prasad. to start his lecture. And over to you, Professor Prasad.
Yeah, I welcome all the students, and let me share the screen. Is my screen visible?
Yes, Professor Prasad.
Okay.
Yes, visible and clear.
So welcome all of you in this magnificent and beautiful lounge. So let me throw a question to you, a guess question, and I will conduct a few polls, not many, but I have 3 polls. This is the first one, and you are expected to respond on this link, pollev.com link, which is shown on the top of the slide. You can give your response there. I'll give you 20 seconds. Okay, so let me share the response with you. So 29%. Oh, 27% are thinking IIT Delhi student lounge. You will be very, very lucky as IIT Delhi student if we have lounge like this. I am a faculty. I also can only dream of such a lounge. There is no, there is no such lounge at IIT Delhi. 5-star hotel is definitely a possible answer, but the correct answer actually is none of the above. So really, this is a recreation of a lounge which was there in RMS Titanic, which was a ship which was built in 1912. The Titanic, the English word Titanic itself means of exceptional strength, size, and power. So you can see the details of the ship, 230 meters long, 25 stories high, and weighted 46,000 kilos. It was the largest man-made object at the time, which was movable, and it was consuming 600 tons of coal a day. So in all sense, Titanic, really big and powerful. This was the first voyage of Titanic. It started on 10th April 1912 from Southampton, and in a week's time, on 17th April, it was supposed to reach New York. However, on the midnight of 14th April, 14th to 15th April midnight, it hit an iceberg, and that was the end of this great ship. In the very first journey, it met with this disaster, and about 1,500 lives were lost. It became a theme of many books and films. I am showing you a clip of a very famous film made in 1997.
Sir Prasad, your sound is not coming, so if you can switch on. Switch on your video sound.
So you can see another picture here. Actually, in the end, the ship broke in two. After hitting the iceberg, the ship broke in two. The question is, why did this happen? A ship is made of thick steel. Titanic steel was more than an inch in thickness, and it was a high quality steel of that time. And it is hitting an iceberg. If steel hits ice, which one do you think will break? Steel or ice? But here, the Titanic broke in two and sank in less than 2 hours. A ship which was supposed to be actually unsinkable. There were a lot of engineering gone in to make it very difficult to sink, but still it happened in a very short time in its very first journey. A very sad story, but a lot of lessons were learned from this disaster. So, to study things like this, the topic which comes in engineering is known as mechanical behavior of materials. And it deals with topics like stress and strain, elastic and plastic deformation, ductile and brittle fracture, fatigue, and creep. Some of these topics we will see as we go along. So it's very, very important to study, because finally, whatever creation you make, it has to withstand these stresses and strain. It has to withstand loads, and it has to perform well in its environment. So mechanical behavior of materials is a very, very, very important topic. You have met with it in your class 8. Mechanical behavior means that force can have an effect on the body. It can change the state of motion, but what is more important, that it can change the shape of an object. So let us see its application in our daily life. We have roti. Let's have roti. Let's cook roti, and I'm making a ball of atta for you, and I'll just roll it into a roti. Just have a little bit of patience in getting my camera on. Here. So here is my roti ball, atta ball, and this is the rolling pin. You have done this experiment, or this experiment is done in your home every day or in your hostels. So you can see that by this process of rolling, the ball has transformed into a disc. I'm not a very good person. You can see I've not got it round. So when you make roti, you are deforming a ball of atta into a disc. And when you remove the force, it does not spring back into a ball again. So this is a kind of permanent deformation. I gave you this example of roti, very familiar, but then it's a very, very important engineering process. So, for example, the car body. This car body is made by thin steel. How do you get that steel so thin? You start actually with thick block of steel and again you roll it. Just like you roll at a ball, you actually roll metal. Of course, you require bigger power and bigger rolling mills, but then thick steel plates are made into thin metallic sheets, which is a very, very important engineering process and produces the thin sheets which you use in these constructions. And this is one kind of deformation where the deformed shape does not spring back. But then there are other kind of deformation you all know, and this is again from your class 9 textbook, that if you pull a spring and then remove the force, the deformation disappears. Or if you squeeze a ball and remove the force, the ball regains its spherical shape. So this kind of deformation is a temporary deformation. It regains its shape when the force is removed. So two kinds of deformation: permanent deformation and recoverable deformation. Permanent deformation is called plastic deformation and recoverable deformation is called elastic deformation. And it's very, very important to keep these two deformations in mind. Both are important in engineering, as you can see, because when you want to use something, when you want to use it in application, you don't want plastic deformation because that is a failure. If the spring deforms permanently, it's failure of a spring. So during application, you require elastic deformation. But when you are forming a material, when you are shaping it, when you are designing for the first time, then you want permanent deformation. Otherwise, you will not be able to create the shape which you want. So both kind of deformation are important. And in engineering, there is a test called uniaxial tensile test. This is a very, very simple test. And it gives you, this test leads to two important properties about material, the strength and ductility. We will have a look at it. So what is a uniaxial tensile test? You actually just have a, let us say, cylindrical specimen of a given length, given initial length L0, and a given initial cross-sectional area A0. What you do is to pull this with a force. The force is only in one direction. It's like pulling a pencil. You can hold a pencil and pull it. So you are applying force in one direction. That's what is meant by uniaxial. And you are applying a tensile force. So this is a uniaxial tensile test. You define two quantities. Engineering strain defined here as change in length delta L divided by the initial length L0. That's the engineering strain. And you take this force and divide by this cross-sectional area, the initial cross-sectional area, you get engineering stress. And you have a graph which plots for you the engineering stress versus engineering strain. And you get something like this. Now, in this graph, the transition point here, up to that point, you can see there is an initial straight line part, that is the elastic part. And where the elastic part ends, I have not mentioned it here, that is what is the stress corresponding to that is called the yield stress sigma y. So you can remember this. We will use this concept later, that the stress corresponding to where the initial elastic part ends. The transition, yield stress is the stress of transition between elastic to plastic. It is the maximum stress up to which the material remains elastic, and it is the minimum stress at which the plastic deformation begins. So that is what is called strength. So the stress of this transition point between elastic and plastic is called yield stress, and that is a measure of strength. And what is ductility? Ductility is shown in the x-axis. Ductility is ability to deform. So the maximum strain which you get at the fracture point, the maximum strain, that is a measure of ductility of material. So both the strength and ductility can be measured from a uniaxial tensile test like this. So let us look at this interesting book, The New Science of Strong Materials. I highly recommend this book to all those who are interested in materials. The New Science of Strong Materials by J.E. Gordon. It's a classic book in the field of material science. Of course, it's written quite a few years back, but still the basic concepts and fundamentals discussed here are very, very interesting. And it's a pocket book. It's a Penguin pocket book. So you can read it in your free time. What I'm more interested is in the subtitle of the book. Why you don't fall through the floor. This seems to be a very interesting, curious question. Why you don't fall through the floor? I'm giving you two options. Floor is rigid and floor is deformable. So let's have the poll again, and I'll give you 20 seconds. So some 36 people have responded. Thank you very much. Let us look at the responses. So we have got both the answers. Some people think that floor is deformable. Majority thinks floor is rigid. We will get the answer soon. So let us analyze the body in a little bit more detail. The forces on the body. I'm getting these annotation requests. I'm going to decline it. So one of the forces which is acting on any body on this earth is its weight, because it's in the gravitational field. So the gravitational force or the weight is acting downward. But why the dancer does not go down or is not accelerating downward? Because you know that there is another force, the normal reaction, which is equal and opposite to the weight. And these two forces balance, cancel out, and that's why there is no vertical acceleration. Now, you have studied about laws of motion. Newton gave 3 laws of motion: first law, second law, and the third law. So I want you to give me an answer again in this poll, that weight and normal reactions, are they equal or opposite? Equal and opposite because of which law of Newton? First, second, or third? So vast majority have answered third law. There are few on first and second law. Actually, first and second law is the right answer. The third law is an incorrect answer, because you should remember, very, very important thing to remember, that action-reaction pair never acts on the same object. Here the weight and the normal reaction are acting on the same body, the same dancer. So action-reaction pair never act on the same object. So the two forces are equal because there is no vertical acceleration. So the two forces have net force has to be 0 and total acceleration is 0. That comes from either the first law or the second law, not the third law. So this was just a warm-up for you. Now, you have studied about the law of gravitation in detail. And you know that weight is due to the law of gravity. Now we also know that normal reaction is acting on it. But what is this normal reaction due to? What is the law for N? The law for W for the weight is law of gravity. What is the law for normal reaction? What is its origin? Where is it coming from? That's the question which we are now considering. So let's look at it in a little bit more detail. If the floor is rigid, there is no way, no physics, no classical physics, no quantum physics, no relativity will give you this normal reaction. A rigid floor just cannot generate a normal reaction. The only way to generate normal reaction is for the floor to deform. It's just like a spring. When you hold a spring in your hand and you deform it, then you will feel a force on your hand because the spring wants to come back to its original shape. Similarly, under the weight of the dancer, the floor has to deform, and when it wants to come back, spring back to its original shape, it creates this normal reaction. So actually, elasticity of materials is the origin of this normal reaction. So whenever you talk of rigid solids, whenever you study rigid solids, actually it's all fiction. Strictly speaking, rigid solid is a fiction. There are no rigid solids, there are no rigid surfaces, everything is deformable, and if you have a rigid solid or a rigid surface, then you cannot explain normal reaction. So normal reaction is produced by elastic deformation. In fact, from the book which I recommended to you, this is a quote: there is no such thing as a truly rigid material, springiness being a property of every structure and every solid. Now, who gave us this law of elasticity? Gravitational law was given by Newton, Newton's law of gravity. The elasticity law was given by Robert Hooke. Now, Robert Hooke was a multifaceted character. He had a lot of interest. One of his interests was observing the sun. And in 1676, he wrote an article on making of helioscopes. Helioscopes? Yes. Helioscopes, telescopes for observing sun. Observing sun is not very easy. You can see, you can hurt your eyes. So special instruments are required, and they were called helioscopes, which Hooke was interested in making. How is it related to elasticity? Well, I told you, Hooke was interested in too many things. So in this article is where he first gave Hooke's law. Because, of course, Hooke's law is not related to helioscopes, but he gave a list of 10 items for future work. In the end of the article, he just listed 10 of his different interests, and all different interests. One of them was the true story of elasticity and springiness. And he gave that true story. He gave that law. How did he give it? This is it. Not joking. This is what he gave. This is what is Hooke's law in its earliest form, by the original author, by Robert Hooke himself. He gave it as an anagram. He wanted to establish his priority and he wanted to discuss it in detail later. But in this article on helioscope, he said that he knows the law of elasticity, and this is the law of elasticity. If you can decipher the anagram, you know the law of elasticity. समझने वाले समझ गए, जो ना समझा
वो चांद खिला, वो तारे हंसे, ये रात अजब मतवारी है। वो चांद खिला, वो तारे हंसे, ये रात अजब मतवारी है। समझने वाले समझ गए हैं, ना समझे वो अनाड़ी है।
Nobody could samjho. Everyone turned out to be anadi. Nobody could decipher this anagram for 2 years. Then, happily, in 1678, Hooke wrote a full article on the elasticity called of a spring. And here he disclosed or deciphered this anagram as ut tensio sic vis, which means, it's a Latin phrase, which means in English, as the tension, so the extension. You know Hooke's law. Force is proportional to elongation. So when a rod or a wire is being deformed under a force, it elongates. The extension, the change in length L, is proportional to the force F. This is what is Hooke's law. F is equal to K delta L, where K is the proportionality constant. We call it force constant or a spring constant. It's also called the stiffness. So stiffness is given as by force divided by delta L. Is stiffness a material property? F is equal to K delta X, fine, discovered by Hooke in 1678. But is it a material property? It turns out that it is not a material property. It depends upon material, but it also depends upon the design of the spring, the dimensions of the spring, the dimensions of the wire which you are testing. So it has both the component of material as well as design. You can think of two springs made of same material, let us say steel. You can make a very stiff spring or you can make a very floppy spring. Depends upon the thickness of the wire and the number of turns in the spring which you add and so on. So engineers struggled. Engineers worried about how to get stiffness of material. And they had to wait almost for 150 years to define a quantity called stress, which we have already defined in the previous slide, force divided by cross-sectional area. And this was done in 1822 by Corsi. And then elongation also was changed into strain by dividing it by the initial length. And then one found that just like Hooke had found force is proportional to elongation, the stress is also proportional to strain. But now the proportionality constant, E, is called the modulus and is a material property. It does not depend upon the dimension of the sample which you are testing. And this is called Young's modulus. So this is a great engineering achievement. About 150 years it took to go from the force displacement mode of thinking to a stress strain mode of thinking. Engineers need both of them. E is called the Young's modulus. Let us get a feel. Let us get a feel of the weight of apple on your palm. So how much is, if I am holding an apple, what is its weight? And what is the stress which it causes? You should think about it. That will give you a feel of the magnitudes which you work with. You do numerical problems all the time in your physics text or in your chemistry text, but you should also have some feel of what these numbers are in real world. So let us do this calculation. So you know, the force is the weight of apple, and let us assume the apple to be 100 grams, so 0.1 kg. Acceleration due to gravity, you know, can be approximated to 10 meters per second square. So the force is simply 1 Newton. So 1 Newton is actually a very small force. It's the weight of an apple. And if I want to find the stress or the pressure caused by this apple on my hand, then all you have to do is to divide it by the cross-sectional area. So here, I take the cross-sectional area as 10 centimeters square, roughly, for my calculation purpose. So you simply divide force by this cross-sectional area, you get 1000 Pascal. So Pascal is actually a very small stress. A kilopascal is what is an apple is creating on my hand. So engineers deal with higher stresses, and in engineering and machinery, you have to have bigger stresses to deal with, and you usually use like megapascal, that is 10 to the power 6 Pascal. Let me take you to a nice trip, a trip to England, to London. But I will not take you to London. I'll take you further north from London to Nottingham. And I'll not keep you in Nottingham also. I'll take you to a suburb of Nottingham, Sneinton. It's a small town, much smaller than London, much smaller than Nottingham. Why I have brought you here? To visit this windmill. This windmill, why to visit a windmill all the way from Delhi? We are going to Sneinton because this is birthplace of George Green. 1793 to 1841. Who was George Green? George Green was a very famous mathematician. You can see it's not easy to get theorems or matrix or laws named after you. Green has all these named after him. But why are we interested here while discussing elasticity? This is because there was a big controversy in elasticity of 15 versus 21. 15 versus 21? What are these numbers? Well, I just showed you that Young's modulus is an elastic constant. So if you want to study the elasticity of material, you need Young's modulus. But you also probably need shear modulus. You also need Poisson ratio. So the question was, how many elastic constants in general will characterize any material? How many elastic constants you really need? And the answer to that was, the science was divided between 15 and 21. Some were thinking that 15 elastic constants were required, and some were thinking even more, 21 elastic constant. On the 15 side, there were big names. Cauchy, who defined the stress, I showed you. Navier, who is also a very famous engineer, so famous that both their names are written on Eiffel Tower. France has this tradition of writing the names of their famous scientists and engineers on the Eiffel Tower. So their names are there on the Eiffel Tower. And here was poor George Green working on that windmill and telling to the world that there are 21 elastic constant, and Green was right. George Green was right, and that's why that windmill is important, where these 21 elastic constants were discovered. They were not discovered in any university or in any scientific lab, or George Green was not a professor in a university. What was he doing? These are the things he was doing. This windmill, which I showed you, belonged to his father. So from his childhood, he helped his father in doing all these things from the age of 5 onwards, receiving the grains, maintaining the sails, maintaining these big stones, grinding stones, and so on. And later on, after his father, he continued to maintain this windmill. So where did he study? Did he go to school? No. No schooling. So he must have had a home tutor or something, good home tutor, because he did so much of scientific research and scientific discovery. No, no home tutor. And his father was anyway a windmill owner, a baker. So he also could not teach him. Nobody really, this is a historical mystery that how this young man, without the aid of any such educational establishments and educational facilities, could do so much of research and so much of work. We complain our school is not good. We come to IIT Delhi, our professors are not good, the labs are not good. But remember that you can do a lot if you simply follow the inspiration and example of George Green. Let's take a cycle ride now. Cycle, you can see in the view graph here, in the bar graph here, that cycle is one of the most efficient, the most efficient traveling vehicle which has been produced by mankind. Most efficient. But we are not interested in that. We are not interested in the cycle ride. We are interested in how the cycle tube or tire fails. Sometimes, you see, you park your cycle, it was all right. You come after 2 hours and the air has leaked out. Air has leaked out. So there is a puncture. Or you can have a big noisy burst. You are rushing to somewhere, you want to reach, you are pedaling fast, and a big burst. Two ways. In both cases, air is coming out of the tube. But in one case, the air is simply coming out. In the other case, there is a noisy burst. So you are all probably waiting for this balloon experiment. I had sent information to you. So some of you must have brought balloon. If you have brought balloon, be ready to do this great experiment of science. I'll do it with you. Let me take a balloon. And then all you have to do, you must have guessed the experiment because I'm asking for balloon as well as for the pin. And what experiment you can do with a balloon and a pin? Simply poke the pin into the balloon. And it's gone. Why? This is a game all child play. Why I'm calling it a experiment? What is so special about this? Actually, this is a very, very special experiment. If you think about it, it's a surprise. The result is, although you have seen it all your life, if you think about it, this is very, very, very surprising. What was I trying to do? I was trying to make only a small hole. Why did the whole balloon burst? Why the surface tore? If I prick a pin into a sheet of paper, I'll only create a hole. What is so special about balloon? That I didn't create just a hole, but tore the whole balloon surface. Let's do few more experiments. So I will do some experiment on paper tearing. If you have brought the paper sheets, which I recommended, you can also do it along with me. So let me try to Let me try to share this experimental station for you. So I have all these pieces of paper. This piece of paper, let me take this piece of paper. This piece of paper is perfect. It has no cracks. And I try to just do my uniaxial tensile test, which I had told you. So I'm pulling it in my hand and pulling it as hard as it seems to be very strong. Oh, I'm not able to tear even a piece of paper. Is the paper strong or I am weak? I tore it finally and it failed in the grip. Now I take another piece of paper and I just made a small cut in it. Just a small cut. And if I pull this, you can see, you can feel also, and I can feel in my fingers. Much less force is required to tear it. Now I do a second experiment. So the first experiment I concluded that if there is a tear, if there is a crack, the stress required to fail is much, much less. Now I have made two samples, one with a small crack and one with a larger crack. So I have cut, but I am using the engineering parlance and I'm calling it crack. So with a smaller cut or with a smaller crack, I apply a force. See, and other thing which you realize, that a crack is there and I'm applying a force, but it's not propagating. So it's not that always a crack will propagate under force. You require a certain minimum force to make it propagate. And if the crack is larger, that minimum force is even lower. So higher the crack size, lesser is the force. Now I have the last experiment which I'll do for you is I have two specimens, both with same size of crack. And you have already seen that if I put a tension, the crack propagates and the paper tears. But what will happen if I put a compression? Then the crack will not propagate. So although there is a material structure, although it has a crack, but if the crack is subjected to compressive stress, crack will not propagate and you are in the safety zone. This is a great engineering wisdom that if you want to avoid cracking, if you want to avoid fracture, you put the thing in compression. So let us conclude. So our first conclusion was comparing two sheets, one with crack and one without crack, and we decided cracks weaken the structure. You know that from your childhood. The second one was with a smaller crack and larger crack, and we again decided that larger cracks lower the strength. This also you know from your childhood because we have experienced the crack and we see these crack propagation and fracture in our life. The final one, which was the interesting one, and I told you that the compressive stress is safe for crack, and this is actually used. And one application I'll show you is your mobile phone screens. These are made of glass. Glass is extremely brittle and prone to fracture. So you make them fracture resistant. And how do you make them fracture resistant? Simply by putting a lot of compressive stress. This stress is already inbuilt into the glass sheet by processes called ion exchange or tempering, and that's why it's called residual compressive stress. And this is what makes your glass safer and less prone to fracture than if this compressive stress was not there. Now, let's look at it a little bit more quantitatively. That is how the stress, we saw that larger the crack, lower is the fracture stress. So how are they related? What is the actual mathematical relation? So this was done by an aeronautical engineer, A.A. Griffith, and he wrote In 1921, he wrote, so in 2021, this is 100th anniversary of that paper in Philosophical Transaction of Royal Society, which is a very famous journal, and he wrote an article, Phenomena of Rupture and Flow. So what did he give? He gave a relation between the fracture stress and crack size. We call this Griffith's equation. You can see here. So fracture stress depends on the crack size, and the crack size is coming in the denominator here. So larger the crack size, smaller the fracture stress. Of course, you have other material property, the Young's modulus and the surface energy also involved there. And here we have plotted that same equation, fracture stress decreasing with the crack size. You can flip this equation and you can solve for C doing your algebra. So you will find that C is 2e gamma by pi sigma squared. Now we call this the critical crack size. So when we interpret it in this mode, sigma f mode, we say that this crack of size C will propagate when a stress of sigma f is applied. If a smaller stress is applied, the crack will not propagate. Crack is there in the paper sheet, but if I am not pulling it hard enough, it will not propagate. Other way of interpreting here is that for a given stress sigma, this will be the critical crack size. So engineers have to worry about this, because in engineering, in a perfect world, in your imaginary world, there can be no cracks. But in an engineering world, whatever you design will always have cracks. And you have to worry about whether the crack present, and your engineering structure will always have the stress also. So what you have to worry about, that whether the crack present is less than the critical crack size. So if you have, for example, this is the stress in your structure, and if you have a crack size of C1, C1 is less than C star, it will not propagate. You are safe. So you can live with this crack. If you have a larger crack C2, still it is less than C star. So you are still safe. But imagine if the crack size you have is C star and you are loading the material with a stress C, then this crack will propagate. And it will propagate and will cause fracture and failure. So C less than C star, C greater than C star is a bad news, is a disaster, is bursting of the balloon. C less than C star is on the safe side, and you can play and you designers want to live in this region. So this is a very, very important development in the engineering science. And note that it was 1921. The Titanic disaster took place in 1912. So in those days, in Titanic time, this understanding of fracture and cracks were not there, was just not there. The science had not developed. So nobody worried about how the steel will fracture under what stresses and in presence of what cracks. You can't make a ship hull without cracks. But the ship will survive if the crack is less than C star, will not survive if the crack is larger than C star. Looking at our mundane bicycle example, so when you have noisy burst, C is greater than C star. So there is a big tear in your cycle tube. When you have silent puncture, C is less than C star, crack size is small and air simply leaks out. Let's now upgrade ourselves from bicycle and ships to planes. What you are seeing here is the first passenger jet aircraft, Comet. It was named Comet, and that's why people are waving, because it was going on its first flight. Previously, the airplanes were equipped with propellers. You remember, you see fan-like thing, which is called propeller in the front of the aircraft. The jet engines were far, far superior in terms of performance. And so when the jet engine came, that was a big news, and it was treated as a new era in civil aviation. 2nd May 1952, it took its first flight. But on the very first anniversary, the first disaster took place. And disaster took place from Kolkata. The then Dum Dum Airport, now Netaji Subhas Airport. One comet took off on 2nd May 1953 and soon fell in the Bay of Bengal. Eight months later, another crash, this time near Italy, near Elba Islands. Another 3 months, the third crash on a flight from Rome to Cairo. People started worrying. Something is wrong. Something is wrong with this design of comet or material of comet. And so it was withdrawn from service. What were the causes of these failures? Well, you have listened to 2 long talks. You must already be tired and fatigued. Metal also actually undergo fatigue. Fatigue is an engineering term, and it means failure caused by repeated loading and unloading. Failure caused by repeated loading and unloading. I show you a situation here. This is a very common situation. No machine you run forever. You switch it on and switch it off. So stress increases and stress decreases. I have marked sigma y, the yield stress, where the plastic deformation will begin. So stress in your object is much less than yield stress. So it's only elastically deforming. There is no worry of plastic deformation. And for this maximum stress, I just gave you the Griffith's equation. You can calculate the critical crack size. And since it is not failing in the first cycle, you know that the crack size, the initial crack size is less than the critical crack size. So if the crack size is less than critical size and it is safe in the first cycle, it should be safe for any number of cycles, second, third, fourth, fifth. But what you see is that after a certain number of cycles, at the same maximum stress, it fails. Fracture happens. Fatigue happened. Material got tired of loading and unloading. How does this happen? Griffith's analysis cannot explain that because we have seen that C0 is less than C star. But then what really happens is what is called a subcritical crack growth. Even though C0 is less than C star, with repeated cycling, repeated loading and unloading, the crack is actually growing. So after some time, it is C0 plus delta C. It is still less than C star. The crack will not propagate fast. So you will not realize. But then finally during the growth process, if it reaches the final crack size reaches C star because it is growing and C star is constant, then CF is equal to C star, fracture will happen. This is called a subcritical crack growth. Why should aircraft body be subjected to fatigue? Well, aircraft is on the ground here, takes off, achieves a cruising altitude, then prepares for landing and finally lands down. If you look at this takeoff and landing cycle, it's also actually a stress cycle. When it was on ground, the cabin pressure was equal to the atmospheric pressure. But when it it was cruising at the altitude, then the cabin pressure to keep you comfortable, and this was also one of the first of Comet. Comet was the first passenger aircraft where pressurized cabins were introduced to keep people comfortable. So if the cabin is pressurized, but outside atmospheric pressure is low, you are at high altitude, maybe 10 kilometers. So the pressure will be very low outside and inside pressure is high. So it is just like a balloon. Aircraft is like a balloon. Engineers will call it pressure vessel. And when you come down, again the cabin and atmospheric pressure are equal. So there is no differential pressure. This differential pressure is actually related to stress. Think of balloon again. When balloon is not blown, inside pressure is equal to the outside pressure. And there is no stress in balloon. But when the balloon is blown, the inside pressure is higher than the atmospheric pressure and it's highly stressed. And a crack can propagate. So when it is on ground, the stress is very low. When it is on cruising altitude, the stress in the body of the aircraft is high and again it is low. So you can see each takeoff landing cycle is a stress cycle. The stress goes from a low stress to a high stress back to low stress. When this was suggested for failure of Comet, there was a dispute. The manufacturers and the airlines didn't want to accept this theory. So one whole aircraft was subjected to fatigue testing. What you are seeing here, picture is not very good, but this is what I could get from the internet. One whole aircraft was subjected to fatigue testing. And how? You watertight, you sealed the whole aircraft and made it watertight, and you will pump water into it. And by increasing and decreasing the pressure of the water, you will load the aircraft body as a fatigue cycle. But water is very heavy, and that will create additional extra load on the structure of the ship. So the whole ship was put inside a water tank. So what you are seeing is this building is a water tank outside an aircraft. Only the aircraft wings are coming out. And in this testing, it was proved finally that comet disasters were happening due to fatigue in the body. It was not understood at that time so well. Now engineers have to take care of this in the design of their structures. Now let's come back to how much time I have?
Professor, you can have another 5 minutes.
Okay. So I will quickly go through this. So you see, ductile, there are two kinds of fracture. I showed you stress strain graph, and I showed you that there is an elastic deformation, then there is followed by plastic deformation, and finally a fracture. This kind of behavior is called ductile. Most metals show this kind of behavior. But there is another kind of behavior where the material is deforming in the elastic regime and finally it fails in the elastic regime also. There is no plastic deformation. Think of glass. Think of ceramic plates and cups in your home. If it falls, it breaks. It's brittle. We call this kind of behavior brittle. It breaks, the plate breaks, but does not undergo any plastic deformation. That's why it is possible to join them with some adhesive like araldite or so. So when you put them together, although it fractured, it did not permanently deform. So the shape was intact, you just put them together and you got the final shape. I have made a video for you. I'll share this for you. This is a video using liquid nitrogen. Let's have some fun. This is a liquid nitrogen can. It has liquid nitrogen. And let me pour some of it. in this container. You can see it's liquid nitrogen, temperature is minus 196 degrees Celsius, and so it's boiling. So liquid nitrogen, you can see it is exposed to atmospheric temperature, so it's very high for it. So everything is boiling. So when I'm putting water in it, actually I'm putting a hot fluid in it. Let's play with rubber band and liquid nitrogen. Let me put some of the rubber band inside liquid nitrogen. This is very, very important. You can see this experiment. Let us see, look at this one. It's just breaking like a glass. It became brittle. Rubber became brittle. Think of this. That one is remembering its shape as it is warming up. This rubber is getting heated, so it is coming. On a Valentine's Day, I decide to present my sweetheart with a flower. Being miser, I do not want to spend on expensive roses, so I just get a flower from my garden and present her. She does not like it and dunks it in liquid nitrogen. And then takes it out and simply crushes it. So flower, and with that, so flexible, gets crushed. That also became brittle. Let's play a bit more with liquid nitrogen. Let me put this balloon inside liquid nitrogen. Let's see what happens to the balloon at such low temperature. As you can see, it's shrinking. So it has shrunk a lot. Let me put some more liquid nitrogen from top. Here is the liquid nitrogen. The balloon has shrunk a lot. Let me take it out. Now let me hypnotize it. अपने स्वरूप को पहचानो. तुम एक balloon हो. वापस आओ. Realize yourself. You are a balloon, not just a piece of floppy rubber. Balloon, balloon, balloon. Since at low temperature, this is nothing very special. At low temperature, the gas had shrunk, and as it is gaining back the room temperature, it is regaining its original volume and shape. Let's have some. So, the important message from that video was that flour, which was very flexible, became brittle like paper. Rubber band, which was very flexible, became very brittle. So, this ductile and brittle behavior, which I showed you as behavior of different material, metal behaving like ductile and glass or ceramic behaving like brittle, actually can be shown by the same material and under different condition. In this case, the temperature. And even steel, for example, And the Titanic steel, for example, can undergo ductile to brittle transition. So at the room temperature, although it will appear like nice ductile material, steel is extremely ductile. At low temperature, it can undergo a ductile to brittle transition and become brittle. So this is the comparison of modern steel with Titanic steel. In fact, people went down and fetched Titanic steel for testing in the lab. And you can see that there was an impact test done, and a modern steel, although it fractured, it did not actually break in two. There is still some connectivity. And there was a lot of deformation, plastic deformation kind of thing. So it was showing a sort of ductile behavior. But the Titanic steel under same condition when it was tested, you can see that it just broke in two pieces with not much plastic deformation. So it was actually showing brittleness. This is again a research done. Don't worry about this whole table. The research done on the Titanic steel, which was pulled out from the ocean bottom, and it was found that Titanic steel, the composition was analyzed and compared with other two steels which are used in modern times. ASTM A36 and lock gate steel are modern steels, and the first row is the Titanic steel plate. You don't have to worry about all the composition, but think of this sulfur. Sulfur is known to cause brittleness. And in modern steel, they are never allowed to be more than, let us say, 0.04% or something. That's the upper limit. But in Titanic steel plate, the sulfur content was 0.06. It's very low. Sulfur, it seems that very low and you can neglect it. But no, such a small amount also. And this is, although small, you can see that it is twice that value which is there in the modern steel. So it was very, very disastrous to have sulfur in steel, which leads to brittleness. So this is one of the Titanic material plate, and the operation of the temperature, low temperature in which it was operating, both caused to the brittleness of the hull plate, causing that failure which we are all familiar with. I will end with this slide of Robert de Ballard. He was the one who discovered the wreck of Titanic in 1985, and this was his childhood dream. Look at his quote. All kids dream a marvelous image of what they want to do. But then society tells them, parents tell them, teachers and professors like us tell them they can't do it. I didn't listen. I wanted to live my dream. So he realized his childhood dream by becoming actually an ocean explorer, going down the ocean, and for the first time seeing the wreck of Titanic. So I end with this: live your dream. Thank you.
Okay, wow. It's been an amazing talk with all these demonstrations and videos, and many students are saying this professors really got some humor. And yeah, so thank you, Professor Prasad, for a wonderful talk. I really loved it, and I'm sure all the students, all the participants, they have thoroughly enjoyed it. And many of the comments now I'm seeing, like, flood comments are flooding in the chat box, like wonderful talk and all. Great. So with this, let me take 2-3 questions
Yeah.
from the
Sorry
second.
for having spilled over the time a little bit.
This is fine. I think we are off by 10 minutes. That's okay. Professor Prasad, I think I picked up few questions, and somebody asked that how can we prevent crack growth from reaching to C star? I didn't understand what is C star.
Yeah. Means
In our
critical.
year.
Yeah. So see, you can do it in variety of ways, and you can actually, many times you can't really do it, but you simply monitor it. So for example, in aircraft and ships, there are a special technique called the non-destructive testing. And they use, for example, eddy currents, or they use ultrasonic waves to find out what is the crack size which is present. And then they test using laws like Griffith. Of course, Griffith is now a very old equation I showed you. It has led to development of what is called fracture mechanics. So they use fracture mechanics principles to determine what is the critical size under those stresses. So if the crack size determined by, let us say, ultrasonic test is less than the critical size determined by fracture mechanics, then you declare that your ship or your aircraft is fine. So it's very, very important. If the engineer makes a mistake in his calculation, you will not like to go into that aircraft or ship. But these understanding actually came much later. Means you saw the dates. Titanic disaster happened in 1912, and Griffith came in 1921. Fracture mechanics developed even later, 1950s. So in Titanic time, or even in Comet's time, these understandings were not so well developed about how the crack is there and how it propagates and what to do about it. So the thing is, and in some cases, like I showed you in the glass, fracture resistant glass, your mobile phone surface cover plate. There, of course, you can try to hold the crack by introducing residual compressive stress. So that's a very, very important technique in engineering. Civil engineers also use it. See, concrete is also a brittle material. It's not ductile. And all our houses are made of concrete. How it is done? Then we are living in a very dangerous, we are living like in a glass house. So the way it is done, that all the concrete which is used is always kept in compression. It is not allowed to come under tension. If it comes under tension, it will crack. But if it is under compression, it is safe.
So can I take two fundamental questions related to pressure and stress? So somebody asked, Susank asked, are the stress and pressure same?
Yes, in a way. In a way, stress and pressure is same, but stress you will study in courses like mechanical behavior, that stress actually is not a scalar, not a vector, but a tensor.
Yeah.
So it has 9 components. And those 9 components, because of some symmetry, reduces to 6 components. So there are 6 different stresses. So in fluids, we talk about pressure, because you have studied about the Pascal's law that stress is same in all orientations. So if if you can see my hand, if I put my hand inside a fluid and put my hand in this orientation, the pressure which is there on my hand is same if I put my hand in this orientation, if I change the orientation. Inside solid, this is not the case. Inside solid, you will get different pressures in different directions, let us say, or different stresses in different directions. So in that sense, stress and pressure are somewhat different, but they are actually the same quantity. That's why both are measured in Pascal. So both are force per unit area, but pressure usually used for fluid, because stress or pressure is same in all orientation. Stress usually used for solids, because it can be different in different directions.
I see. I think a quick clarification on your slide that you told stress is proportional till the yield point. So is it up to proportional limit or yield limit? The question was Suraj.
That's a good question, and I think textbooks all discuss that. See, there is something called elasticity and something called proportionality. Most materials have this Hooke's law, or proportional behavior till elastic. till they are elastic. So if the material is following Hooke's law, the elastic limit and proportional limit is the same. If the material is not following Hooke's law, sometimes materials can be elastic, like rubber. Rubber is elastic, but it does not follow Hooke's law. There, the force and elongation are actually not proportional if you stretch the rubber band too much. So in that case, you have crossed the proportionality limit, but still you are within the elastic limit. So there can be a distinction. That's a fine distinction. But for many metals and ceramic materials, the elastic limit and the proportionality limit are more or less the same.
Okay, great. So now I think we move on to the panel discussion session. So I'd like to invite both the speakers, Professor Ganguli and Professor Prasad, to be visible to the audience, and I can pick few questions from the chat box. So it's more like a general question to Professor Ganguli. In such low temperatures such as Iceland, how do the inner fluids of human body or animals main fluid or do not become, or anyway, the question I rephrase it.
Depth.
So,
Okay, if I understand, it is
I
like
think you got it.
how. Shall I answer?
I think you got the question. So it's like human body and animals. How do they survive?
Marine animals at the depth of sea, how do they survive the pressure? Am I right?
Exactly. Yeah, yeah. The
Okay.
temperature and pressure.
Yeah. So the temperature, of course, because they are built of certain layers of, they have a lot of fat and many other things, the skin, etc. That is the takes care of the temperature. The pressure is more important. How they take care of the pressure is that naturally at deep sea marine animals, every marine animal cannot live at deep depths. Different marine animals can live up till certain depths. So the ones which can live at very deep depths, they have something special in their body. They have what is called swim bladders. You know, swim bladders are like a lung which will have the pressure, the inside is the same as the external pressure. So it is balancing the external pressure with the internal pressure in the swim bladder. This is one thing. But apart from that, there are other things. For example, your organs can be crushed by the pressure, right? Our organs will all get crushed in that heavy pressure. They have a chemical in the body. It is, I think, called trimethyl something. I'm not getting it exactly. You can check it up. That chemical somehow blocks that the proteins, etc., everything stays normal in the body. So nature has done that. It is not there in us. It is there in them. It takes care that the proteins and all don't go out of shape. It maintains the shape even at that high pressure. That's the second thing. And there is a third thing. You know, when you do deep sea diving or somebody like if you go underwater, the chances are nitrogen gas getting into the blood. Our blood needs oxygen. That's why the blood, how do we breathe? The oxygen is carried into our body through metalloporphyrins, which is in the blood, which is in your hemoglobin. You know, you have this iron. That's why you have to take iron tablets, though you have lack of hemoglobin. That picks up the oxygen. It moves in the blood and goes to and delivers at the right places oxygen. But if nitrogen is there, you know, at when the oxygen pressure goes down, as you go into deep sea, the concentration of oxygen in water decreases, and your blood will have problem. You will not be able to breathe, right? But they have a situation where they don't allow, the body does not allow nitrogen to get into the blood. So nature has done, I gave you three things: swim bladders, a chemical called trimethyl something, and the body does not allow nitrogen to go into the blood. That's how they survive at depths.
Yeah. So the next question is, the question was asked by a person many times, like, why don't we use tantalum carbide and hafnium carbide for heat seals?
Yeah.
Since
So
they can withstand up to 4,000 degrees Celsius.
So whenever you are in making anything, shape, aircraft, it's business, right? Or spaceship. So you have to use the right material at the cheapest cost.
True.
So tantalum carbide or hafnium are one of the most expensive materials. And you don't need 4000 centigrade because at re-entry time, the nose cone is around 1500 Celsius. So why should I take a material which costs me so much to withstand 4000? I will use it where 4000 centigrade is required for that. But there I don't need that. So I'll work with reinforced carbon composites and other things.
So the next question is, what is the use of this Nomex aromatic polyamide? I think it's the insulator.
So that is the one of the best insulations for fire and heat resistant.
Yeah, the transformers and all that we're using. Yeah. And there's one very relevant question to in the current time, which is like, we have this antibacterial fibers, but is there any antivirus fibers so that we can fight against the COVID or something?
Yes. So there are many antiviral fibers now, and there was a special drive by Government of India in the last after COVID time. Many proposals, many research projects were done. Lot of antiviral masks and all are in the market. If you Google from India, also many Indian institutions have worked, including IIT Delhi and many others, which have made antiviral masks. So on the fiber of the mask, the cheap mask which you wear, see, masks today in the market are probably 100 types of masks are available. So the more expensive the mask will be, there will be some antiviral coating, there will be some triboelectric generator which destroys the virus on approach. There are many things. The simplest mask that you use is basically protects through the textile. It does not allow the the virus to enter. But there are antiviral masks which destroys the virus through some chemical coating, through some other kind of charge being generated on the surface. So there are now hundreds of masks in the market, and India has also done a lot of work. A lot of masks have been now commercialized, and you can buy expensive. You can buy a mask for 10, 20 rupees probably, and you can buy a mask for 400, 500 rupees also. So there is a lot of variation, the kind of mask that you want to wear.
So I take the last question. I mean, there are many questions, interesting questions, but I think due to the time constraint, we'll not be able to address all of them. So the last one is, what is the phenomenon behind superconductors, how they leviate, and why only in lower temperatures? So I think you have explained, or if you'd like to add something.
Superconductivity, two key points. If any material is superconducting, then it will be perfect conductor. There is no resistance to flow. And the other thing is, it will be a perfect diamagnet. That means no magnetic field line can go through that material. Okay. And why does it levitate? Because of the diamagnetism. So diamagnetism means if you bring a magnet close to it, the superconductor will try to throw away the lines of force. So there will be a repulsive force. That's why it levitates. It goes up because there is a force which is pushing it away from the magnet because the superconductor is throwing out the lines of force. The other thing is asked is why you have to cool it, because there is no material today, maybe you should work on that, which works at room temperature. So all known superconductors work only at low temperature. So this is a great challenge to all scientists. They are all working. So if you know 100 years back when superconductivity was discovered, the temperature at which superconductor was working was at nearly 4 Kelvin. Today we have superconductors which are working at 160 Kelvin, 125, depends on which material. But maybe after another 10 years or tomorrow somebody finds a material which works at 300 Kelvin, then everything will change in this world. All your house wiring, everything will change because superconductors do not have resistance. So if your home wiring is made of superconducting wires, then you will have no power load. Your electricity will go to zero. Electricity bill will go to zero.
Yes. So thank you, Professor Ganguli. I think I'll take a few questions for Professor Prasad. There is one question from YouTube by Suho Bera. The solidity of ice in Atlantics was more than steel. At any point of time, steel will break the ice when force applied, but here how the solidity of ice became more than steel. So I think Did you get the question? Related to
Yeah,
the,
the same question which I was raising, that
yes,
why steel hitting an iceberg
exactly, the main
is
theme.
breaking. So actually means ice also at very low temperature is a very strong material. But if you see the details of the collision of Titanic with the ice, the iceberg also, little bit of it broke on the surface. It didn't fracture like the Titanic ship itself, but it little bit fracture. So actually both suffered damage. But the Titanic's damage was more disastrous because what really happened is that it was designed to be unsinkable ship because it had 16 watertight compartments in the hull. And the design was such that even if 4 of them get flooded, ship will still be floating. But the crack was such, the initial crack was such that 5, more than 4, 5 or 6 started getting flooded. So that part started getting heavy, and the whole thing then actually was like, since the ship is floating and one side is becoming, and there is a crack also, and one side is getting heavier yeah, because of the damage. So then that led to an overall, like you are bending a pencil, so stress is there in the front because of the flooding, and the other side there were propellers and other heavy machinery. So the whole ship was put into a bending kind of a stress, which led to a further crack propagation and breaking into two. So yes, means comparison with ice and steel is interesting. Ice also broke to some extent, but not the whole thing. It also depends. You see, when you will go into detail, how is the stress distribution? Because when the contact is there, when the impact is there, the stress will not propagate immediately to all the parts.
Yeah.
So it's actually a surface contact. So at the surface, the iceberg also broke. And at the surface, just like Titanic also, the impact of iceberg didn't break the whole Titanic in one go. It initiated a crack. And then that crack propagated, which led to the disaster.
True.
Many things of Titanic are still intact at the ocean bottom, and people are exploring and bringing them up. And there's question also of ownership, who owns them, and so on. So it's a very interesting situation.
Yeah. So there is one common question, although it's very crazy question. After seeing your demonstrations, now people got too much excited, and they're saying if it is, what would happen if we dip our hand inside liquid nitrogen? It's a crazy thing.
Don't do it. The simple
Somebody asked
answer is
like,
don't do it. Professor Ganguli also will recommend, like, liquid nitrogen is a very important liquid in both
Actually,
chemistry.
if you like somebody touched, I think Rajesh, you touched it. If you touch it and take it out, nothing, it will not happen. But if you keep it for long, little bit longer, then if your finger will get frozen, and then if I just touch it like this, your finger will flow.
Yeah.
So
Cold burn. I
you
think the
can
cold burn is the phrase.
you can just touch it like somebody touched it just for a second or few seconds, then you will feel the cold. But you are not supposed to keep your finger inside. Then it will break after some time.
I think cells will die, Ashok.
Now you will have many, depends on how long you are keeping. First, initially you will have cold burn, and then it will become brittle, and then it will break.
So,
But one thing I wanted to tell you with this experiment, actually, I was planning to show this experiment. Good, I didn't. Rajesh showed with the rubber band. I was going to show with the O-ring. You know what is the O-ring? It is put like a gasket between two metal joints, and that was a reason. There was a space shuttle called Challenger. The Challenger, while taking off in 1986, exploded. And you know why it exploded? Because it was shown later on that one gasket was not proper, and that gasket actually was exposed to cold weather, and it broke. That gasket broke, and the Challenger exploded because it immediately inputs a lot of things. So one gasket, one O-ring, which costs maybe few rupees, can cause $1 million disaster if not done properly. So what he showed, he put rubber band and it cracked. That gasket, same issue. And that's how, when NASA did that inquiry, the scientist leading that inquiry was Richard Feynman of Caltech.
Yes.
And he showed that in the demonstration in the White House, probably. And he put that what he did, put rubber band, he put that O-ring in liquid nitrogen and showed that it cracks. And that's what caused the disaster of the Challenger in 1986.
Yeah, there is a movie also, a Hollywood movie, Challenger Disaster.
Right.
Beautiful one. Anyway, so I think let's conclude this kind of panel discussion here because we are running a bit late. And it's a time to thank many people. I mean, there are many hands for making this event so successful. So first of all, I'd like to thank both the speakers, Professor Ganguli and Professor Prasad, for taking your time out for this beautiful event, I must say, and fantastic talks. I really loved it, and I'm
Both
sure
did
I'm
PhD from Indian Institute of Science.
Yes, Indian Institute of Science, yeah. And Professor Ganguli is now the deputy director in our institute, and he has many meetings apart from doing, contributing to science. He has many administrative works. Despite that, he has kind of joined us and gave
Just
up.
want to share one nice connection between me and Professor Ashok. Our first meeting was not in he just mentioned ISC. Our first meeting was in ISC Bangalore.
I said ISC.
IIT Bangalore, yes.
Yeah. He joined as a PhD student. I joined as an MTech student. And
Okay, wow.
and we were both placed because the hostel rooms were not available immediately. We had to go and register and get the hostel. So initially we were placed in a common room. So we had to sleep on the common room floor, and both Ashok Ganguli and me were sharing the same common room. And if I remember correctly, correct me, Ashok, that everyone else got the rooms except me and Ashok. We were the last to get the rooms. So we stayed probably the longest. So our first meeting was, and first sharing was in the common room of ISC Bangalore, Indian Institute of Science, Bangalore.
Yeah, so in that sense, it's nice to have you both on the same podium for this.
And I think we both joined IIT Delhi also on the same year, probably
1995, yes.
Yeah,
1995.
Mhm.
Yeah.
So it is
thank
nice
you.
that we are both put together in the same session.
Exactly. So thank you, professors, for the
Okay.
fantastic thing.
Yeah.
And we'd love to have many such lectures in this weekend lecture series, so that we can kind of motivate or inspire the young minds, so that they take science, or they get more excited with scientific discoveries and stuff. So whenever you get a chance to do scientific experiment or get exposed to science, please do so whenever or wherever it is possible. And with this, I'd like to thank Professor Pritha Chatterjee, our professor in
Pritha Chandra.
Pritha Chandra, yes, professor in the humanities and social science, and she is now dean of outreach program. She has been always there for this event and shaping it up properly, and bringing it to you eventually. And I'd like to thank more people who are involved in this program. The Professor Soumik Siddhanta is assistant professor in the Department of Chemistry, and he is taking care of all these technical things in the background. Professor Divya Nair, who is also helping us in many ways. Mr. Gaurav, who is taking care of the entire thing, like starting from connecting students to creating links, and eventually helping in smooth running of this program. And a special mention to Renu, who has created all these videos as well as the pictures, the posters. And we'd like to thank many mainstream print media who have covered the Sci-Tech Schemes events, and now I think they're helping us spreading the words across the country, across the globe. So we'd like to thank them especially. And we'd like to have more electronic media to spread the words, so that we can even reach a broader audience in the future. Of course, we'll have many more exciting ideas, exciting creative things that we'll add onto it. And last but not least, I'd like to thank, or we would like to thank all of you for your enthusiastic participation. And I think we all enjoyed the session, and hope to see you again in the next talk. And probably there are many people whom I didn't mention by their names who were involved in shaping up the entire thing. And I'd like to thank our director also, Professor Ramgopal Rao, and IIT Delhi for hosting this kind of fantastic event. So with this, let's conclude this today's session. And I'd like to tell you that take precautions, stay safe. COVID is not over. So wherever you are, be safe. Okay, and take care. Bye bye. Thank you.
Bye bye. Thanks. All the best to you, everybody. Bye bye.